Well, take a look now. We're on lesson 3, and I have a delightful news for you. I don't like it, but you will like it. We're not doing this lesson. We're not doing this lesson. So we just go lesson 4. It's just not in the curriculum for 20-1. But for those of you that think you're going to be future astronauts or whatever, I would probably try some lesson 3 if I was you. No, only their heads grow. Big ego. All right, so today we're going to learn about the absolute value transformation. And you already are aware of this. Okay, we've seen this before. They're reviewing for you the definition of the absolute value equation here. Okay, so you can take a look at it. When are you the original? When the original is bigger than 0. And then when the original is smaller than 0, you multiply by a negative. So let's take a look at this investigation. They want us to graph y equals x minus 1. So this is our original function. Go to your calculator and graph this. And as far as copying into the workbook, you can do that. I think I'll just explore. And I've shown you this already, so it's nothing new to you. So you should feel comfortable with this. I'm just going to quickly change my window to match the window of the workbook. Okay, I've typed the function into y1, and I've adjusted my window to look more like the workbook. Okay, so you have this equation right here, or this graph right here. So what do you see? A straight line. Obviously the function is linear. The y-intercept is -1, so I'm just going to jot down y equals mx plus b for you. Again, y equals mx plus b. We can see that the y-intercept is -1 and the slope is 1. You can see it's going over 1, up 1, over 1, up 1, over 1, up 1. And if you want to take a look at the table, you hit second graph, and you can see exactly what I'm saying. What's happening as x goes up 1, y goes up 1. As x goes up another 1, y goes up another 1. So that's the slope. And what's the x-intercept? When x is 1, y is 0. That's the point we're interested in. Okay. So let's copy down our table onto the page. So when it's -4, it's -5. Okay, and then it's just going up 1 every time. So up 1. This is the point that we're interested in, the x-intercept. So we can plot that point. And of course you can plot the y-intercept as well. This one here. This is the y-intercept. And of course, once you have 2 points, all you need to do is connect with a straight edge. So you would grab your ID card or whatever. And we have our line. Now, staring at this line, we know that it goes off into infinity both directions. We have this y equals x minus 1 function. Now what happens when I do the absolute value transformation? What happens when I do this? What happens when I slap on those absolutes? Some part of that graph is going to bounce back. Good. So which part? only the portions of the graph that are experienced negative, right? If the graph has y values that are negative, it's going to say, nope, that's not cool, flip up. So all we have to do is do a mirror image. So if we are doing a mirror image, you imagine like this mirror line. Like for example, this spot here at -1 on the y-intercept, where would it reflect to? Scare me, Mahad. Right there. And over here, when x is -1 and y is -2, it would pop up to +2. And then you would go ahead and you would make that line. Oh, smartboards. I gave up on it. Just kidding, I smashed it. Just kidding, it's fine. I just leave it at home now for some reason. Okay, so I've drew in the red line to mirror the negative portions of the black line, but we know that the absolute value function of this original function is going to be the whole thing, right? It's the whole thing. I just want to show the effect in red. Okay, so again, making the connections here, especially you guys going into 30-1, 30-2, this f of x represents what? In terms of x or y? It's the y. So if we're going to slap on absolute values here on f, that means y. We have to slap the absolute values on y. So let's take a look at what's going to happen to our table. What happens to -5? It becomes 5. -4 becomes 4. -3 becomes 3. -2, you guys get it. What happens to these positive ones? They stay the same. And that is why all this has stayed the same. That's not been mirrored or anything. Okay? Any questions about that? This is sort of reinforcing how I introduced absolute value in the first place. Let's try it for this function here. Let's try it without the calculator. So they've given you the original curve, x squared minus 4, and they're saying that the graph is here on the right. Why does this make sense? What are these x values on the intercepts? X equals plus and minus 2. How would you get those x-intercepts from this function? Difference of squares, you'd have that factored, and you'd have those zeros, those x-intercepts. Those zeros are so critical because we're doing absolute value where we're interested in the switch between positive and negative. So the switch between positive and negative is obviously at 0. So these become critical to understanding this idea. So you have the two x-intercepts, the two zeros. That's what they're called, two zeros. And below that, you see the negative, and above, you see the positive. What's an interesting point down here? Obviously, the starts with, what is this? In this case, the y-intercept happens to also be the vertex. It's not always going to be like that, but it happens to be this time. And what is that y-intercept? -4 when x is 0. So why is it -4? Look at the equation. What is always the y-intercept? Thank you, Zara. The constant. All right, so you basically have a good understanding of this quadratic graph. Now let's switch to green, and I'll talk about what's going to happen when I take this original function and let's slap on the absolute values. So what does that mean when I slap on these absolute values? What's going to change to this? Will these positive versions change? But only this negative portion, right? So where will negative 4 end up? Positive 4. And then you just use symmetry, and you have this new graph that's going to be identical where the original was positive, and it's going to be reflected where the original was negative. Okay? So where the original is positive, stay the same. Where the original is negative, now you have a lot of options here. You can say reflect in x-axis. You can also say multiply y coordinate by -1. It's going to do the same thing. So just take down those notes, and then we're able to do these questions. This is all this lesson is. It's pretty straightforward. It's a very short lesson. And once you jot down these notes, what you'll see on the next page is exactly what I just said, right here. So you wrote it twice, which is okay. Yay! So this is really formal, and mine is more layman. So if you want to just read a layman's approach, and then if you want to read the formal approach, they're both there for you. So in each of these cases, sketch the originals. I'll start over. For each of these examples, you're going to take the original graph, and you're going to do what's called a absolute value transformation. Okay, absolute value transformation. And I bet you guys are looking at me like this is child's play, because it is. I guarantee you guys in elementary school, maybe even junior high, you did like reflections, rotations, and translations. You probably remember that. But you're just mirroring over a line. So I'll use another color. And you can see, is that challenging? Is it challenging? No. So why don't I reflect this stuff down here? Why don't I do that? Because it's what? It's already positive. You don't need to worry about it. So it's an interesting thing where you just basically just find the x-intercept and then reflect all negative portions. Reflect the negative portion. That's all it is. So like let's look at part B here. Is there even an x-intercept? So I guess I don't even need this. Find the x-intercept. The thing about the x-intercept though is like it's a place where you know that you should stop. So don't go past the x-intercept and start. So all this needs to be reflected, all this needs to be reflected, and okay, stop. Over here there's no x-intercept, so every single part of this graph is negative. So when I do the absolute value transformation of this graph, all of it gets flipped. And again, you have this like mirror line, right? So do you see how there's a gap between the mirror line and the start of the function? So you need to include that gap here, and there it is. And I missed, so I suck. It's just the pixelated smartboard, so let me try that again. When you're drawing quadratics, like you can start at the vertex, so let me do that more formally. Start at the vertex, and then just draw like a curve like this. And then start on the other side, and then draw that curve like that. Try to get some symmetry. They don't do this, okay? they don't do that. They forever infinitely spread out. So quadratics will, at the vertex, will always just continually spread out. Okay, like, okay. Sometimes I see this, like, hello, it's like devil horns or something. It doesn't work. No. All right. And they want us to talk about the domain and range now. Okay. Let me just zoom out so we can see everything. Okay, so domain and range is very important. If you still haven't mastered that, let's see if we can get it today. We're going to consider all the graphs and then their reflections, or their transformations, and compare the following aspects of the graphs. Okay, so let's do the domain for A. I'll do black for the original. So what's the domain for the original thing? And what is domain again? I'll write on the whiteboard for you guys. So the definition for domain is set of all x values. And that means input. All the input. And when you see arrow on the function pointing left and pointing right, that means all the x values work that way. Here's 0. All the x values work that way. So like Daoud is saying, the domain would be x element real. And again, if you want to do that formally, this symbol, this, sorry, I just got a little dizzy there. I don't know why. This symbol here is like it's like a squished E, and then I do a double bar, and then the R. And again, what does that little E stand for? Element of, and then you put the set here, whatever the set is, right? It might be like a bag of marbles, or it might be like Daoud's jewelry box, like whatever you want it to be, right? So you say like, you know, pearl necklace inside Daoud's jewelry box. Eh? For his future wifey. I love it. Okay, so let's take a look at the Y. That's the range. So again, if you're forgetting this stuff, you have range. Definition of range is set of all Y values. And of course, these are your outputs, all the possible outputs. It's not one output or two outputs, it's all possible outputs. So looking at these Y values, what do you see? Could you have like Y 100? Could you have Y negative 1,000? What Y values work? And if you struggle with this, you can use a highlighter and see that like this is the highest Y value and this is the lowest Y value. So you would look at that range, that interval. Range is a bad word. Actually, they don't use this in post-secondary. They just use domain, codomain. So it's a bad word, but in high school, range, all Y values. So we go with R, colon. And you notice why I go with the double R here for the real, because you go to write range, and this is why in post-secondary they don't use range, R and then the real R. It gets confusing. So you say Y is element real, you get that wrong, because it's not all real numbers. There's only a certain amount of them that work. So which certain range, which certain interval? What is that value? I can't even see that. It doesn't tell you? Well, this is 2. And I'm assuming that this is like roughly the same. So let's go -2 to 1, 2, 3, 4. So you say range is Y. less or equal 4, but greater or equal negative 2. And when you go to do the domain and the range, and the values are set between a low and a high, you can always aim your arrows to the left. Okay. So what happens when we do the absolute value? So let's switch color. So now we go from the black graph to the black with red graph. So like this. Oh, like this. So what's the domain of the new function? Did it change? No. So the domain's identical. So what are you going to learn about absolute value? Domain is not going to change from the original to the new. Domains do not change. But does the range change? Yes, because the range is the y value. So now, on an absolute value, you'll never be less than 0. So at worst, like you're 0. And then the high here is 4. It won't always be 0, but it'll never be below 0. So we can see that the range will be affected. I don't know if you put E affected or A affected, but oh, whatever. Let's use affected. And then domain is unchanged. We're not in English class. Shaq. You love English class. And Mahad, you love English class too. Okay. Now let's take a look at x-intercepts and y-intercepts. X-intercepts and y-intercepts. So, still working on this function here, the first one. X-intercept. Did it change? So on the start, it's -3, 0. Am I right? Am I right? Okay. On the new one, is it the same? Okay, so you can make a generalization that probably, does that even change it? Does the x-intercept change? And why? Because it's what? It's like a reflection from the source kind of thing, right? It's weird. How do you reflect anyway? What do you got to do to those y values? Good. And what happens when you multiply 0 by -1? You're so excited. Okay. Now the y-intercept, a little bit of a different ball game. What's the y-intercept? The original was +2, right? And on the new one, it's also, I should change color. Oh, it's also +2. So did it change? So what could we say? It never changes? What? It didn't change on this one, but could it? Yeah, it could. Why? You mean y-intercept? And how do you change the y value for absolute value? You have to multiply the y by -1. So it could happen, right? And did it happen on this graph, the second one? Yeah, the y-intercept did change. So the y-intercepts can change. The x-intercepts will never change, okay? The x-intercepts will never change. And you can see that the domain, let's just do this one quickly. The domain is x real. And for the new domain, is it the same? So the domain's not going to be changed because the domain is x. X not going to change. But y can change. Okay? So did the range change on this second graph? Yes. What was the original range? Y greater or equal to whatever this is? Is it 2? Looks like 4 up there. So 1, 2, 3, 4. So y greater or equal 1. And then you can put comma y real, but we haven't got space. Then when you go to do the next one, instead of all the y values being bigger than 1, all the y values are less than -1. So not only did the sign switch, but also the value. Okay. X-intercepts won't change, Y-intercepts can change. Okay, perfect. Shall I go to the next lesson, or do you want that to be it? That's it? All right. Let's go to the homework. And it's a short lesson, so let's take a look at... oh yeah, do everything. There's only 5 questions, seven questions. Okay, and I'll get you started. Look at these cool graphs. These are real. To make this graph, you would have to do piecewise. So from x values of 0 to 2, you'd have like a negative slope linear. And then the second piece would be from x values 2 to 4, you'd have like a positive linear. And then you'd have constant, and so you could generate that easily. Yeah. And the c, you'll learn later, will be like cubic, 3rd degree polynomial. Anyways, so what you're going to do is you're going to take another color, hopefully different than the black ink, and you're going to trace. You take another color and you start on the positives, and then you reflect. When you see negative, you're going to reflect. So it goes up 3. Then it comes back down, and then you go back up because you're happy with positive. And then right here, you're going to just like pretty tight. Okay? So let's get started with that. And then, yeah, this number 2. Consider some random function. Explain why the absolute value is less than 0 has no solution. Because the absolute value is never less than 0. Okay, so let's do the homework, and I'll stop the video.